In this highlight video, we're going to talk about our first two reactions of alkanes, hydrohalogenation and halogenation. After watching this video, you should be able to predict the products and the reaction mechanisms for the addition of hydrogen halides to alkynes and for the addition of halogens to alkynes. Alkynes are similar to alkenes in that they have carbon-carbon pi bonds. They're different, however, because they have two pi bonds and can therefore react by either adding once or twice. Here's an overview of the reactions that we'll be taking a look at. Starting with terminal alkyne, we can add two equivalents of HX, giving us this product here with two halogens attached to a single carbon. This is the hydrohalogenation reaction. We can also add just halogens, chlorine or bromine, to add four halogens. This is the halogenation reaction. Hydration reactions of alkynes give us products that are slightly different than what we might expect. These two are hydration, and notice that the final products are either a ketone or an aldehyde. We'll talk about these reactions, or this reaction, in another video. Like with alkenes, the hydrohalogenation reaction of alkynes is an electrophilic addition reaction. The first step of this reaction, just like with alkenes, will be protonating the pi bond following Markovnikov's rule, which will give us a cation that looks like this. So this is a little bit different. This is called a vinyl cation. Vinyl means on a double bond. The vinyl cation here is actually sp hybridized. So this makes it less stable than a normal secondary carbocation. This reaction can continue. That cation can then react with bromide, just like we saw with alkenes, to finish our first addition step. So this would have two H's here. So this is called a vinyl bromide. So if we add just one equivalence, or one molecule of HBr for every one alkyne, the reaction will stop at this stage, at the vinyl bromide. However, if we add more HBr, so either 2 times or an excess, then this reaction can continue on further. If we do that, we add HBr. So because we still have a pi bond, the reaction follows the same type of mechanism again. It's going to protonate, but this gives us two possibilities for the carbocation. Either the new H can go to the same carbon as the bromine to give us a carbocation like this, or the H can go to this end to give us this carbocation. So to predict the relative stabilities here, we could either go just straight off of stabilities of carbocations. This is primary carbocation. We know it's going to be very unstable. This one, if we think bromine has the same effect as carbon, we could think of this as being tertiary. But in fact, the bromine has more effect than you might think about, because this bromine has non-bonding electrons around it, and so it can donate electron density to that carbocation. This gives us just a different resonance form, because all we're doing is moving electrons here, and gives us a carbocation like this. So this tertiary one, this one is actually stabilized by resonance. Okay, so it's going to be the predominant carbocation. That carbocation again can finish the reaction, react with another bromide. We can show this either reacting with this resonance form. If it reacts with that carbon, these electrons will go up on the bromine, or we could show it just reacting directly with this resonance form. Either way, what we'll get is a dihalide with both bromines attached to the same carbon. So, just a couple of notes. It can add either one time or two times, depending on how much HBr we add. And it is going to follow Markovnikov's rule. Okay, so we're always going to end up, though, if we add two, with both bromines attached to the same carbon. Let's work a couple of examples. In the first example, let's just say we're adding HCl. Let's say we're adding one equivalent. So that means we're adding an equal amount of HBr as we have, or HCl as we have the alkyne. So this should add one time, follow Markovnikov's rule, and put our new chlorine at the more substituted end. So we will get this vinyl chloride. In the second example, notice we're adding excess, so that means we're adding enough that the molecule will react with as much HBr as it can. So it would react once to give a vinyl bromide and react a second time to give us this bromide like this. Both bromines on the more substituted side. In the last case, notice that this alkyne is symmetrical, so the H could go to either end, the bromine goes to the other end. But if we add an excess here, we know that both bromines will end up attached to the same carbon. Whenever we have two of these groups, bromine, chlorine, attached to the same carbon, sometimes it's called a geminal dibromide. Geminal means on the same carbon. The halogenation of alkynes follows a mechanism identical to that for alkenes. And again, this reaction, depending upon how much halogen we add, can add either one time and we can stop, or it can add two times to react as many times as possible. So if we add only one time, or an equal amount of chlorine, we will just add one equivalent of chlorine, and it will give us a chlorine on each carbon. All right, it's also still an anti-addition. If we add an excess, or 2 times, say bromine this time, it will add yet another time, and we end up with 2 of the halogens on each of the carbons that used to have the double bond. All right? So we've looked at 2 reactions of alkynes, and they really follow the same process, the same outcome as we saw for alkenes. It's just that we have 2 pi bonds, so they can react twice.